Raman Scattering. Yes, correct. Yeah. Thank you very much to organizers giving possibility to give a talk here. I don't know, my topic is maybe it's a little bit something far from the quantum devices, but still quantum. So, still quantum. So, last year I give a here talk, just announced the results. So today I want to just make some report the scheme, how this works really, because this multipoint green function or correlation function, nobody really calculates, I think. Yes. So okay. So my co-author is Professor Karowski from Berlin. Yes. And Free University, and Alexei Tsvelik from Brookhaven National Lab. So we have two papers, PhysRev B and Nuclear Physics B, published already. So, and then I will explain what we're doing. So first, these are my content. It will be something introduction and motivation, and so on. Yes. So let's start the introduction. So we will know from the physics that complete set of the correlation function, if you calculate, then you get entire information from the system. Exists a famous theorem of the Weitmann, constructive theorem of the Weitmann, when he's saying that if you have all correlation function or green function, then all theory is done. But in fact, of course, difficult to calculate this is, I will show you the simplest example here. So, but also the experimental point of as teaches our co-author Tsvelik. Unfortunately, in practice, few such a function can be measured by available experimental technique. Only 2 points. They probe something in neutrons scattering. They measure 2-point function. Only exists Raman scattering, which is you need a 4-point correlation function. I will show you later that this Raman scattering really is something proportional to the 4-point green function. Yes. So Raman scattering is really exceptional case. And higher order the correlation function carry information about the nonlinear dynamics, which is especially important and interesting in strongly correlated electrons. It is also an interesting theoretical problem, saying that such models are usually require some spatial non-perturbative approach, where we can calculate the multipoint correlation functions. Two theories exist, such a 2D CFT, massless gas. This is famous Belavin-Balakov-Zamolodchikov paper. As you remember, it is a conformal field theory. Then you have really infinite dimensional symmetry, Virasoro algebra. Then you have non-trivial differential equation for the 4-point or higher correlation function. 2 and 3 point immediately fixed by conformal invariant. But 4-point or higher is complicated. You need some special, some null vector called, then you can calculate this correlation function. And many cases this done. For famous Fatev, that Dotsenko paper, when they calculate this endpoint correlation function. So this conformal field theory really is a unique place in a quantum field theory that you can have many of the correlation function. But this is in a massless point, in a conformal point, very something, and also in 2-dimensional. In higher dimension, we don't have such a things. We have, for example, higher dimension. You have just the something free propagator, nothing else. Or you have the for Schwinger-Dyson equation, which you cannot solve, never. So second coming the second coming the again 1+1 dimensional integrable models. In these theories, we have infinitely many conservation laws. So these conservation laws allow to calculate, in some sense, the two-point scattering matrix, which is solution of the Young-Baxter equation. Yes? But nothing else. You don't have anything to calculate the correlation. You know, real field theoretical models, you cannot calculate the correlation function. In this reason exists this four-factor approach, which is done separately. Yes, later, something. Originally, this was again in this as conformal field theory. In integrable massive quantum field theory, also this idea was first in Polyakov in Chernogolovka, Landa Institute, and created his student, and then this continued to in Berlin, Karofsky, Weitz, and co-authors, and later Smirnov. Fyodor Smirnov did a lot of things, and finally formulated this sometimes called Smirnov axiom, but usually we call Karofsky, Weitz, Smirnov equations, which today I will not write because I don't have time. We last year give a lot of talk here and explain all the details. So today I will be busy just calculation of the correlation function. So the four factors will be solution of this equation. So many years we calculate this four factors, and now we're going to use it to purpose to calculate these green functions or correlation function. So we did this in three models. This first of all the usual Ising model quantum, yes. Then you can diagonalize because it's a free theory. Is an S matrix equal -1. So simplest example. But even this case is complicated. You will see how to complicate to calculate multipoint correlation functions or green functions. Here is a no pole, nothing given, no dependence from the theta. So this is a non-interacting massive Majorana fermions. Second, Sange-Gordon model, which also easy S matrix, something is not the constant, but no poles. It's essential. No poles. Here also we calculate multipoint, 4-point function or 3-point function. And finally, Z3 Potts model, Ising model. Here exists one pole. This also we calculate something. These are really complicated, starting complication. So these three theories, the S matrix is diagonal. There are no backward scattering. It's essential. So we learn just this in this simple case to calculate, which I will present the scheme of calculation. Yes. Z3 Ising model. Yes, this is paraformant theory. Continuum limit, scaling limit. Yes, exactly. So this is we have S method, which wrote I think André Sveka in Brazil. He proposed the S method for this theory. Zien, in the case of Zien. So about physical application now. Physical application for this Z3 and Sange-Gordon, we don't know something. But for the 4-point correlation function for the order parameter, we know we get the application for the Raman scattering, which I will show later. So now, how to calculate how to calculating 2-point functions. The 4-factor, I already told that this is something local fields, vacuum state, and because we know the two-particle S matrix of solution of Young-Baxter equation, and then you know the in-out state. It means with a known state, as usual, what is 4-factor in nuclear physics? With a known state, you want to get some feeling from the local operators phi, yes? So these are 4 factors. But this is a meromorphic function usually, solution of this Smirnov Karofsky-Weiss equation. Yeah? So this is, if you have, then you can calculate 2-point function easily. Because you need to calculate 2-point function, yes? You push here here, and you get 2-point function. Yes, so. And integral or all theta something here. So this is a 2-point function. Only problem to investigate all this behavior in infinities or all possible asymptotics. So this is a meromorphic function. But when you have such a complicated, when you're going to calculate multi-point correlation function, you have such a more complicated 4-factor. Then this is a singular, because always you need to calculate the integrals over all the rapidities theta here. Yes? So you have actual infinities, because if one of the rapidities is equal to another one, then you have actual infinity in integrals. What to do? So you have to define the analytic continuum, this object, in order to calculate the correlation function. So this we're doing if you know the perturbation, so you know you push the theta in other side. So it means we should use the crossing formula. So this is just definition. So we have some formula for the crossing formula, complicated. So idea is to you changing the thetas to the here, then we have like 4 factors. But this is a distribution already, you will see. Look, so now for simple case, for example. So theta 1 here, theta 2, theta 3. So this is a I pi minus E should be epsilon. Theta 2, theta 3, and also 2 disconnected part. So here delta functions. So already, so this function we express in the language of the usual 4-factor, but still we have delta function on epsilon prescription, which make the object generalized function. So, and then already our all integration, which was before here just minus plus infinity, but theta variables, now this becomes some complicated contour integral. So this is my axiom. So to calculate Green function, we have such a T product of the local fields. Then we have to use the already calculated 4 factors to start calculate multipoint correlation function. So let now, this one I forgot to write down here, sum of integrals here. He is also integral something. He should be also integrals or all thetas. They also. So they also you have to, what you're doing, you such a identity, you inserting the inside of the fields, and then start using the crossing formula, then using the calculated 4 factors. And then step by step you're calculating the multipoint function. But this is a non-trivial object, you will see. So this is, and theta is this is the step function, yes? Because of this time order. This is so we're calculating Green function. Yeah. So this technically we separate some object which is proportional to delta function, which is written there. So again, 4 factor is such a meromorphic function, which all this complicated function will be expressed to the in this way. So we use 3 when one theta is the left-hand side. Yes, then we have such a formula. Again, is a e plus here, and delta function, 2 delta functions. This is disconnected part. And second one, we have here opposite. Theta 4 is other side. Then we have another function. And theta p plus and pi minus, this is shifted by epsilon. And theta, this is delta function. So this now, look, this right-hand side is generalized function. So always we have to have complicated contour to take this integrals over theta, which is essential part of our calculation. Yes. So now let's starting now 3-point green function generally. So we yes, yes. No, this is general, but this disconnected parts. This is general. Yes, this is delta function, yes. Exactly. Right. Yes. Yes, this we know, yes, of course, yeah. Usually this contribution from this, I mean, is zero. You have to forget this, most part, but sometimes happens that you have to take into account this also. Yes, you have to use the, you have a 3-point function, but already with this shift, yes? I pi means changing sign of the momenta, and then epsilon prescription, yes? So which makes something, how you should avoid this actual infinities. This epsilon prescription teaching you how to do that, right? So now we start 3-point green, 3-point. So what you do, you putting the, let's look the theory which the non-trivial 4 factors local field has only odd one, for example. In this case we look. So then you see this such a contribution. This in example Ising model is the order parameter. Epsilon is the density of the energy. So second one. Now, yes. Now there's a 4-point. There's a 4-point. Then you have more complicated structure. Then you have 3 points. Something. 1 point here. This constant. Then 3 points. So always we have to use the formula which we have. So now let's now scaling Ising model. So then the usual Ising model, you move to the scaling, and then you introduce such a field. M is a mass and C is some constant. So mass is h minus g, yes, something in the range of the Ising constants, and this energy density is you can express in the range of Majorana fields. So now then already we know the 4 factors of the order parameters. N points is just product of tangencies. Odd numbers, no, even numbers. No, odd numbers, sorry. This odd number, N is odd here only. The even number form factor is 0. Opposite the mu, this order parameter has opposite the even number of the 4 factors. Epsilon also. Epsilon has only 2 points, other is all zeros. So now we calculate such a 3-point green function. So epsilon 4 factor is just simple Sench function. Now, so if you calculate this now after some, so what you're doing, you putting there all these things, here, and then making some Fourier transform, calculating all integrals, and then you get such a result for the 3-point function in a spatial limit. So Cvilik teaches us for experimental point of view, the essential, you take the special part of this momenta go to 0. Only the time part will still in the, should survive. Then it's more interesting for the experimental point of view. So then we have such a object for the phi epsilon. This is only one. So we have even 10 terms something. You have to calculate all possible changing fields and also momentas. We calculate all possible this permutation and then arrive to this formula. So if you calculate 9 terms, which h is something, h plus, for example, such a function, also another is the h minus, which where is something he is minus and he is minus. So very complicated things. This Zweig believed that this function should be possible to measure an experiment like nonlinear sociability, but very complicated function. So look, such a behavior you never can calculate. We get in perturbation theory such a behavior, for example, arctangents. Non-trivial function coming up. Even theory with a spin equal smartness equal -1, just a constant. Not something complicated which we're going next to learn to calculate. But this is simplest case, how complicated function coming out. So next we start to calculate now 4-point order parameter. Yes? So 4-point order parameter you need to, again, so you putting there all possible and the expression which we before had, yes, where it was the 4-point here. So you put here this intermediate state, this identity, then you start to calculate, yes. Start to calculate this using the crossing, put here, and collecting them. Terms a lot, so you have to collect all the terms, and very carefully, because everywhere you have to take into account the singularities, and then collect the terms. Yes, so this is a but this calculation is a unique calculation in quantum field theory. But you don't have any other possibility to calculate multipoint or Schwinger function, sometimes they called. So now what we get, you see, we get this 3-point was. Now, yeah, this is a 4-point. So now this we get. So you see this term and epsilon to minus epsilon. There is G is this function, and listen, before was yes, yeah, yes. More? What? This is you see. This is sigma. This means order parameter. Yes, this was before was the. I wrote the 4-point function here. Yes, so instead of this phi, this sigma order parameter, and 4-factor is I wrote something later. Something 4-factor of this. This is this f sigma. Yes, it's like here. So 4-factor is here. So just you have to use this odd point 4 factors in order to calculate the multipoint function. So you this is 3-point. Yes. So here. So you have many permutation. Yes, you have so all possible now permutation over k. Any terms exist here, where j is this integral which we calculate successfully. It happens that that is not so complicated to calculate, in fact. Then we, yes, after calculation we get some beautiful function, something. Look at this. Look, this again. This behavior of this such a behavior we have here. This is this, yes, and logarithms also. So this is of course not exact, but this is such a 4-factor is a infinite sum of the perturbation Feynman diagram calculation, which you never calculate something in normal way. This is sum. So, but now I want to present interesting points. So people, of course, the calculate Raman scattering, just quantum mechanics comes out. First calculation was Heisenberg did. Yes, it's because what you did, you have to light is interacting with the media, then going out. So how to calculate this this such a cross section? This is really something huge work. Yes, but this all our lives connected to Raman scattering. So we see everything because of Raman scattering. So, and many people doing Raman scattering. So this Hrachya, Babujian, Frenges, and Deveryux, they have some beautiful formula. So they're saying cross section of the Raman scattering. This omega is ingoing, F is outgoing, frequency of the photons. Then this cross section is proportional to the 4-point function, some special imaginary part of the 4-point function. I wrote it the sigma. Generally, this is some the general means such a you have such a diagram something. So some imaginary, some special imaginary part of this. This is this K, yes. So if you, it means that you have some media. So insert some material. So if you know how to calculate the 4-point green function, take the Fourier transform of that, then take some spatial limit, then you can calculate the cross section of the Raman scattering. So yes, yes. Yes, exactly. Yes, yes. I will tell you. Wait, you see, we have candidate for that, right? This formula brought these pupils. You see, this is they have good experience to calculate and compare with experiment. This is this long time life experience. You see, look, you have to. Mu some constant. Yes, some constant. Omega is ingoing. Yeah, right. Exactly. Yes. Yes. What? This this exactly the imaginary part of this 4-point function. So you taking something. You was at 4-point. You see, is the first something moment, a second, third. Yes, in this case, these are order parameter. In the sigma, in this case, Ising model. But they believe. You see, look, wait. They exist how to exist the treatment how to Ising model the sigmas treat that how calculating how interacting with the photons exist. Yeah. By no. I think something else. But you see, this people's right, of course, not Ising. This they mean the essential 4-point function in the media. This what formula? Of course, they don't have any idea about Ising model. This Ising model, it's our idea. But these pupils, of course, here they mean something 4-point function. 4-point function, some inside of the media which you have. Yes. Photon is running. No. These three, usually they have to normal, 3-dimensional. But we have 1-dimensional something. Wait, you see. This is our explanation for Ising model. We get some something experimental suggestion for that. But these people are doing completely real physics. Pasha. And this formula, nothing to do with Ising. We wrote, this is our idea. But this formula general, forgot the sigma. And this complicated formula means that you have to calculate real material 4-point function. Yes. For this material, exists some material which are real excitation there. And you have to calculate the multipoint green function. You see? Here's the material, Pasha. This multipoint 4-point function is here. Is material. How you calculate this is also your problem. So this is something optical theorem. This is something well known. I believe that something. This is formula. I think some implementation of the optical theory. What sigma? No, sigma is in our case. Sigma is order parameter. You see, these people wrote this formula generally. They have good experience to write many materials. They have calculating in perturbation theory. Do you have to calculate such an object, 4-point function? Take the Fourier transform and take such a special limit. Pasha. Exactly. Which coupled to light, yes. 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 Psi, you mean. Psi, you mean. Epsilon. This epsilon parameter. Density of the... Yes, exactly. Yeah. So, Pasha, are you satisfied now or not? Okay. So, you have to take such a limit. So, delta 1, delta 2 go to 0, some special limit, which we did. So, we have calculation already this object for point, which depend from the theta. So we take such a limit and calculate this XR, which is the almost the cross section of the Raman scattering. So yes, so then one can calculate this. Then we get such a beautiful non-trivial answer with the gx. This is a step function. Yes, step function, Heaviside function. And here x divided by m. Yes, look, every way is 2m. Look, something. So this is answer for the cross section of the of this. No. So everything is okay. Bracket is here. G is here. Yes. So yeah, maybe. One bracket is missing. Yes, sorry. Yes, here and here. 1, 2. 2G, second G, yes, so this is clear. I forgot one bracket. No. Present transparent knows for such a formula. So such a 5 halves have here. Look here, this such a non-trivial behavior we have here. So he is Pasha. So now our friend Svelik, which is familiar for these materials, he proposed the candidate for this experimental realization. This material, columbite, yes, another one. This material, exactly that material which was observed, Zamolodchik of Ising P mesons. Yes, experimentally observed. It means in Ising model in external magnetic field in a special point, as you remember. So he believed, already now he convincing the experimentalist from the Johns Hopkins laboratory to measure in this material Raman scattering. Because in this material, so already P meson is observed, so it means they are quasi one-dimensional materials. I don't know. This is asked to Svelik. In the latter, yeah, maybe. In the latter. Yes, yeah. Because one-dimensional, yeah. This is. So this material is well known. So if we need something more calculation, of course we can more time calculate. Our calculation is valid when something this omega A, omega F is smaller than 4m. It's if you need more stronger calculation, we can add more terms to compare with experiments. Yes, so I'm coming to the end. So we developed a technique to calculate multipoint Weitman or Green function in quantum field theory one dimension. So we insert this identity and use the crossing formula and calculate multipoint function. We also did, of course, with the St. Gordon and Z3, but calculation much more complicated. So I don't present here, but that calculation exists our paper. In next, we want to These three theories which we calculate was just diagonal S matrix. One is S equal -1. St. Gordon is some simple, no pole, and Z3 only one pole. So this, yes. So now we want to enlarge our this technique in the case of ON sigma model, this with backward scattering, when you have non-trivial big S matrix. Yes, this is ON Grosne-View, or SON chiral Grosne-View, and so on. We want to make this is a next. We will with Karofsky make to this work. So thank you very much.